Hey guys, today we're going to be talking about LR circuits. So obviously there's two main parts to this, having an inductor and a resistor. So talking first about a resistor, we'll just use a couple of equations to kind of give us a better idea of what that is. So we know R equals resistivity times length over area. And as well as we can use voltage equals current times resistance. So for this first one, we know that resistivity is the ability of a material to resist the flow of an electric current. So we use that ability to resist it, and that relative to the length and the area of whatever the material may be gives us the resistance of that given thing. And as well as we can use voltage and current to know how that relates to resistance and to solve for that as well. And then the other part of it we know is the inductor, which is L. And inductance, the basis for it comes from Faraday's law, which states that a change in magnetic flux will induce an EMF, which we see in this equation, where we use EMF equals negative L times the change in magnetic flux over the change in current. So we see how those relate and affect each other with that. And again, we know that inductance is measured in henries and resistance is measured in ohms. And a couple other key equations to use for this, first of which is tau. Now tau is the time characteristic, the characteristic time or time constant. It's referred to as either, and that is equal to the L over R. And the last equation we need to know is to how to relate it to current. So we can use I equals I naught, which is our maximum current, times 1 minus e raised to the negative t over tau. And that's what we can use to find the current at a given position or time, and we'll do that here in a minute. And so using those, we know that often we've seen, for example, in a diagram or when you're using resistors in circuit questions, you'll see resistors labeled like this. So that's going to be our resistor. This is our battery, obviously. And then how we do an inductor in this, which is a little bit less common, sometimes you'll see it as a coil, just kind of rounded. So either, a lot of times you'll see it like this, and that's how that will be characterized in a circuit diagram. So that is our inductor, and this obviously is our battery. So we're going to do an example here. We're going to say that our voltage of the battery is 15 volts. We're going to say our resistor is 50 ohms. And our inductor is 10 Henry. So for this, we're going to solve for three things. First, we're going to solve for our tau. So the tau, if we remember, it's a very simple equation. So it's L over R. So in this situation, we would just take our inductor, which is 10 henries, divided by our resistor, which is 50, which would give us a tau of 0.2. And we know this is the time constant, so that's just measured in seconds. Next, if we were to try to find the current of this, the equation we use frequently, which is V equals IR. So if we put this in terms of the current, we flip that around to do I equals V over R, which we already have those two variables, which would be equals 15, which is our voltage, over 50 equals 0.3 amps. And the next question we're going to do is a little bit more complicated using that last equation we talked about here. Is if you want to find the current after a certain amount of time after the switch has been turned on. So we're going to say 25 milliseconds after the switch has been turned on to start the circuit, what is our current? So we're going to use this equation. So we remember we have I equals I naught, and that's our maximum current, which is our 0.3, 1 minus e raised to the negative t over tau. So we're solving for our I. Our I naught is 0.3 times 1 minus e raised, our time is 25 milliseconds, should be 0.025 seconds, over our tau, which we calculated before as 0.2. And when we calculate that, that gives us an answer of 35 milliamperes, or 0.3 amps. Or excuse me, so 35 milliamperes, which tells us how long after that switch is turned on. In 25 milliseconds, that's how much current is flowing in the circuit at that point in time. Now to kind of give us a better idea of why it matters or what the currents are used for, a lot of times what we'll see more often is an RC circuit. So RC circuits are much more common and have more practical uses, but one of the biggest differences is how they respond to a change in current. Because a resistance has a capacitor, which we see here, which a capacitor turns on, right away or doesn't. The key about the inductor is its resistance to a change in current. And so that has that bigger effect where it happens more slowly, whereas it resists that change. So RL circuits, just kind of give you an idea of what they're more often for, are commonly used in wire coils or solenoids, as well as chokes of luminescent tubes. And we can also see applications of RL circuits in an AC circuit because it helps to reduce that voltage without the loss of energy. So there's a little intro to you on how those LR circuits work. Hope that's helpful. If you have any issues solving that problem, leave a comment below. Thanks.